Hello, everyone. Welcome back to our class on elliptic curves. We're going to continue talking about elliptic curves over local fields. In particular, we're going to talk about more about points of finite order on over local fields. So remember, we started with our setup. K here is a local field, and you have the ring of integers, the maximal ideal, a uniformizer, and the residue field. And given an elliptic curve over K, then we constructed what we call the minimal model, which is just an elliptic curve still isomorphic to it over K, but with coefficients in the ring of integers. And among all those with coefficients in the ring of integers, we pick the one with the minimal discriminant, the minimal valuation of the discriminant. Those we can reduce modulo M, and then we get an elliptic curve over the residue field. Well, a curve over the residue field, which might be singular. So to deal with that, we define three auxiliary groups: the points that are non-singular in the reduction, the points of non-singular reduction, and the kernel of reduction. And then what we proved is what we call, or what I call, the fundamental sequence in elliptic curves over local fields, which is this sequence that relates the points of non-singular reduction and the points of that are non-singular over the residue field. And then the other part, now finally we connected this to formal groups by proving that the kernel of reduction is actually isomorphic to the and so this is the formal group, or the group associated to the formal group of E. Okay, and then using what we proved about formal groups and about those groups associated to formal groups, we're going to be able to say something about torsion points on E. So let's get started. So what I wanted to prove, I stated this last time, is this theorem, or this proposition of a point of finite order. We're going to prove that if you have an elliptic curve over K, and M is an integer relatively prime to get the characteristic of the residue field, then the subgroup E1 has no non-trivial points of order M, and if the reduced curve is non-singular, so if you have an elliptic curve, when you reduce, then the points of order M actually inject into the points in the finite field. Okay, so there is an injection like that into there. Okay, so let's prove that. So on the right, you can see an example we already worked out last time. For that proof, it's pretty simple now because we've built all the machineries. First, we know that we have an exact sequence. We know an exact sequence that goes like follows, from the kernel of reduction to E0 to the reduction, the non-singular points in the reduction, right? And on the other hand, we also know that this is isomorphic to the formal group, or the group associated to the formal group. But we proved by a proposition, I believe, well, is in the book at least, is 4.3.2 part B. What we saw is that EM has no points of order M where when the GCD of M and P is 1. So it has no prime to P torsion. Okay, so that proves A. Okay, so that is part A, that checks that there is no points of order M on E1 because E1 is E hat. Okay, And for part B, if the reduction is non-singular, then we actually have a better improved formal exact sequence that goes from E1 to E to the reduction, because E0 is all of E and ENS twiddle is all of E twiddle. Okay. But then we have that, well, the M torsion in particular would map into the point of the reduction. But if there is no point of order M in the kernel, then the points of order M must inject. Okay. And E1K M, which is, if this is reduction, this is the kernel of the reduction map. The M torsion in the kernel is trivial by A, then it must mean that the M torsion actually injects. Thus, the M torsion injects into the kernel, into the points of over the residue field, because there is no intersection with the kernel, or the intersection with the kernel is trivial. So we have that injection. And that is one of the, just a very, very useful tool. The fact that the M torsion injects, as long as you have your reducing modulo prime of good reduction, and that prime and M are relatively prime, then the M torsion injects into the group of points over the finite field. So we used that last time in this example. So in the previous video, we worked this out in detail, that if you have, for example, this elliptic curve over Q, there is non-singular reduction for every p bigger than 3. You see from this that the equation is minimal at every prime, so it's minimal over qp at every prime p. We computed the number of points for 5 and 7, and then we saw that then what this says is, for example, for the q torsion, where q is not 5 or 7, the q torsion would inject into here and here, and therefore the order has to be a divisor of 6 and 13, so it divides the GCD, but the GCD is 1, so there is no Q torsion. If Q is 5, then what you can do is inject the 5 torsion into the reduction mod 7. But then a group that is a 5 group has to be of order 1, 5, or 25, a billion. So it has to divide either it has to divide 13 and 25, and therefore it is trivial. And similarly for 7, there is no 7 torsion, so there is no torsion of any kind. And then you have that the full torsion over Q is trivial. Okay. Let me give you one more example, which is the following. So let's work backwards and to start with an elliptic curve. Like this, and then compute number of points. Okay, so I'm going to put up a table of primes, and also the number of points in the reduction modulo p. So I have the primes 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, and compute number of points. So I've computed this ahead of time, and what I get is 5, 5, 5, 10, 11, 10, 20, 20, 25, 30, 25, etc. Okay, so knowing what we know, the torsion, so the the torsion, at least the pieces that are relatively prime to each one of those primes, has to inject on the in the group of points over FP. And then you see that this group of points over FP is a multiple of 5 every time, except, weirdly, 11. But 11 is actually a bad prime. It's a prime of bad reduction. Okay, so if you check, it is a prime of bad reduction for this curve. So I'm going to eliminate it. I'm not going to look at this column. Okay, so if you remove that column, now every single number of points every time is a multiple of 5. So what this tells me is that maybe then there probably is some 5 torsion floating around, because you see that there is the 5 torsion would inject into the 7 torsion, into the reduction mod 7, for example, and there you go, and it is divisible by 5. The 5 torsion would inject into the mod 3 reduction, and there is a point of order 5, and so on. So this gives you a hint that there could be torsion defined over Q, and indeed, we will actually figure out how to do this. So indeed, oops, not writing great today. That's right, indeed. We will see that for this particular elliptic curve over Q, there is a point of order 5. Okay, which is why you see that the points, the number of points modulo P for every prime of good reduction is a multiple of 5. Okay. All right, so you can use this to prove that there is no torsion, and then you can also use this to give you an idea of, like, if there is torsion, what kind of torsion do we have? Okay, you see that from the reductions, if there is torsion, it must be 5 torsion and nothing else, because otherwise we would see, if there was 7 torsion, we would see multiples of 7 here also, but we don't see that. Okay, so so this is mostly about the prime to P torsion. So let's see what happens at the P torsion of an elliptic curve over a local field. So this is the following theorem. At the end of the formal groups, we also dealt with this. It gives the formal group theory gives a bound on the valuation on elements that have a power of P torsion. So we're going to use that. So assume the characteristic of the local field is 0, and the characteristic of the residue field is positive P. Let E over K be an elliptic curve given by Weierstrass equation with each AI in R, and let P be a point of exact order M. Well, first of all, this is actually also about the integrality of the coordinates. So it turns out that if M is not a power of P, then the coordinates of your point are integral. Okay, so no P in the denominator. And if M is a power of P, some power of P, then pi to the 2r times xp and pi to the 3r, we're going to define r in a moment, r in r with, this is the greatest integer function, the valuation of P over P to the n with R equals, which is an integer. Okay, so what this says is that, so for example, if R is 1, it says that the worst that it can be is a pi squared in the denominator of X. And if R is 1, pi cubed is the worst denominator that can happen for Y. Okay, so this is telling you where to look. If there are going to be points of finite order, how far do you have to go in your search according to how bad the denominators may get. But also in particular, the first part is telling you that a lot of the torsion is actually integral, is defined over the ring of integers. We will also in the next chapter put this together over the integers, or over Q and over the integers, and see what this says. But I will also give you an application of this in a moment. So here is the proof of this theorem. So let's start first. So if x of p is in R, then notice that y of p is in R, or y of p satisfies, so from here, you can see that if x of p is in R, then y satisfies that equation, and that y equation, in that equation in y would be a monic quadratic polynomial with coefficients in the ring of integers. Therefore, y itself is also integral. Okay, so y of p would satisfy monic quadratic polynomial over R, and therefore y of p is also an integral coefficient. Okay. Alternatively, if y the square of p is, it satisfies, once you solve for, it would be something of a y plus b with a and b integers, and if the valuation of y was negative, then this equation would be impossible. Because the valuation of the left-hand side would be smaller, more negative than the valuation on the right-hand side. Okay, so it has to be that the valuation of y is bigger or equal to 0 for that equation to be feasible, which is the proof that also when I say that if it satisfies a monic polynomial, then its integral is basically the same proof. Okay, so so if x is integral, then y is integral. Okay, so let's start by assuming that x is non-integral and see where we get. So assume that x of p is not an integer, and therefore the valuation of x is negative. We have not assumed that the equation was minimal to start with. Okay, so even if it's not minimal, the theorem holds, but I'm going to move to a minimal equation, because if the equation is not minimal, then and I have a new set of coordinates, x, y, x prime, y prime, that are minimal coordinates, then what happened is that I had a model over R, and then I divided by some u coefficient to get a smaller discriminant. And when that happens is that the x and the y get divided by something. So I'm subtracting I'm dividing by another multiple of the uniformizer, the x and the y. So what happens is that the valuation of x, which was already negative, is actually even bigger, or the valuation of x prime would be even smaller than the valuation of x. And similarly, the valuation of y would be even bigger than the valuation of y prime. So that is also negative. So might as well assume that the equation was minimal to begin with. Okay, so suffices to show the result for minimal equations. Okay. And now the trick is that since the valuation of x is negative, and we have an equation y squared plus a1xy plus a3y equals x cubed plus, and this is in x, okay, x squared coefficients in x. This is this poly, this is quadratic poly in x. Then what happens? This is the smallest, or the smallest in negative valuation happens here, okay, and it has to match a valuation on the left-hand side. The valuation of the right-hand side, the valuation of the left-hand side has to be the same. But the minimum, if y had, for example, if the valuation of y, or the valuation was minimal here, that coefficient is going to have a smaller valuation. How to say? So if you do a computation, if you do an analysis of where the minimum valuation would be, it has to happen here, because if it was, because if it was here, then the valuation of y would have to be less than the valuation of x, and therefore the valuation of y squared would be even more negative. So what happens is then that the valuations match of y squared and x cubed. Okay, so the valuations of y squared has to be the valuation of x cubed, and then what happens is that 3 times the valuation of x is twice the valuation of y, and the valuation of x is negative. Okay, let's call it, and the valuation of y then has to be negative. The valuation of x is an integer, the valuation of y is an integer, so the valuation has to be a negative multiple of 6. Okay, so this has to be something like minus 6s for some s bigger or equal to 1. Okay, so that the valuation of y is minus 3s, the valuation of, so now this is minus 2s, and this is minus 3s. Okay, so let me repeat that here. So we were working with a point. So we assume that we have a negative valuation. So we have a point, k, order m, with negative valuation. So it is not an integer. And we arrived at the conclusion that 3 times the valuation of x is twice the valuation of y is minus 6s. Okay, and notice that then if you write x of p, y of p 1, if I multiply through by pi to the 6s or pi to the 3s, is going to be pi to the 3s x of p, pi to the 3s y of p, pi to the 3s. Now, pi to the 3s times y of p, this is integral. This is, in fact, a unit because the valuation is 0, okay? But this, the valuation of xp is 2s, so this is going to be in the maximal ideal, and this is going to be in the maximal ideal. So this actually reduces to be 0, 1, 0 upon reduction. Okay. So what that tells me then is that actually P is in the kernel of reduction. But we know that the kernel of reduction is isomorphic to the maximal, the formal group, or the group associated to the formal group, which has no M torsion. With relatively prime to the characteristic of the residue field. Okay, so if you start with a point that has non-integral coefficients, it cannot be of order m, where m is prime to p. Okay, that was what part A said. Here is part A. If m is not a power of p, so if m is not well, if m is not a power of p, then there's going to be something that is not a power of p. But in any case, it has no m torsion, therefore, this point cannot be of order, it cannot be non-integral. Or if it is non-integral, then it must be a power of p. All right. So this proves part A. And okay. Oh, by the way, remember that this map went, P is sent to minus x over y, and then if you compute the valuations, what is the valuation of x over y? That is the valuation of x minus the valuation of y, which is 2s minus 3s, it's s, and therefore x over y is in the maximal ideal, which is another way of saying that it maps to E hat m. But now we're going to use this for part B. If the order of P is a power of P, then in the chapter of formal groups, what we saw in this proposition in particular said that S, which is evaluation of minus x over y, that valuation had to be less or equal to a bound nu of p. So the valuation of p divided by p to the n minus p to the n minus 1. We prove this using induction, right? And therefore, but notice again that note that pi to the what is it, the valuation of pi to the what were the valuations? The valuation of this is 2s. The valuation of here is minus 3s. So pi to the 2s times x of p and pi to the 3s y of p are integral, and therefore if we put r to be the greatest integer below this fraction, then it is also always true that pi to the 2r x of p, y to the 3r y, oops, not y, pi, y of p, those are also integral as claimed. Okay, so that just follows then from the formal group that if you have a non-integral element and it is a power of p, then we have a bound on the valuation of the element that corresponds to that point in the formal group. And again, what this is saying is the largest power of pi that can be the denominator of x, and the largest power of pi that can be in the denominator of y. Okay, and it's just a bound. There might be points that fit that and points that are integral completely. But it does happen that those bounds are attained in some cases. So for example, so let me give you an application of this to what we care about, which is to start with an elliptic curve over Q that has a Weierstrass equation over the integers, and let P be of exact order M. Okay, some M bigger or equal to 2. So first, if M is not a power of a prime, then x of p, y of p are in ZP for all primes p. But if integer is in ZP for all primes p, then it cannot have any denominators. Any denominator that a 2, a 3, a 7 is in the denominator would prevent it from being Z7 or whatever. If there is a p in the denominator, it cannot be p-adically integral. So if it is p-adically integral for all primes, then it has to be an actual integer. So the coordinates are integers, okay? And then maybe just for clarity, let's change this prime p here to a q, say. Okay, it doesn't matter. So if it is not a power of a prime, not for p, not for q, it cannot be in zq. It cannot be, it is always in zq for all q, for all primes q. If m is a power of a prime, then well, how much is the largest integer in the valuation of p over p to the n minus p to the n minus 1? We're talking about qp here. So the valuation of p is just 1. And this is going to be 0, is going to be smaller than a half, smaller or equal to a half if p is, let me actually do it in another way. It's actually going to be 1 if p is 2 and n is 1. And that's the only way that that fraction is 1, and then the greatest integer is 1, and otherwise it's 0 otherwise. So even if p is 2, if n is 2, we already have what, 4 minus 2. So we already have a half in there, and that is the greatest integer now is going to be 0. Okay, so this implies two things: that if m is bigger or equal to 3, then the coordinates are integral, and if m is 2, if it's a point of order 2 exactly, then well, then this thing is 1, and therefore what that says is that 2 is squared. The uniformizer here is the prime 2. So in this case, P is 2, N is 1. P is 2, so this says that 2 squared times the x coordinate of the point and 2 cubed times the y coordinate of the point are integers. So the best you can say is that there might be a 2 in the denominator, and that there's going to be a 4 in the denominator and a 8 in the denominator of y. Okay, and you might think like, well, maybe that doesn't happen. All this was a bound, but this actually happens. So for example, if you take the elliptic curve y squared plus xy equals x cubed plus 4x plus 1, it turns out that it has a point P, which is minus a fourth and an eighth, which is a point of order 2 over Q. Okay, so that can happen, but any other torsion point would have integer coordinates for an elliptic curve defined over the integers if the coefficients are in the integers. It turns out that we will see that if the coefficients are, if the Weierstrass equation is actually in short Weierstrass form, this cannot happen. Then even the 2 torsion has integer coefficients. Okay. Right. So
can I ask a quick question about that?
Yeah.
So we've just proved that all over Q with the Weierstrass equation over Z, that any point that has torsion greater than, so any non-2 torsion point will be integral. That's what we've just proved, right?
Yep.
Okay. Wow. Cool.
Yep. We will. This is not stated as a theorem because that will be there will be a more general proof, that is the Nagel-Lutz theorem, and we will prove it there or we will state it there in more generality. So that will come back in the next chapter, which is over a global field. We'll start talking about elliptic curves over Q, and we'll state this again in that format. But that is what we just proved. This proves that any point of order m, so any point of finite order, at least 3, the coefficients have to be integers. And if it is a point of order 2, then the worst it can happen is that you have a 4 and an 8 in the denominators. This is sort of like weird. This doesn't happen often. So in most cases, you have that all the torsion is defined over the integers, but you have to be careful that there might be at least one point defined over actual Q. Okay, so let me stop there. And then in the next video, we'll talk about the action of inertia on the Tate module.